Let's try a few more offbeat examples with our limit comparison test. We'd like to decide whether the sum from 1 to infinity of 2 to the 1 over n squared converges or diverges. Now as n approaches infinity, 2 to the 1 over n approaches 2 to the 0, which is 1, so we would expect for very large n that the terms of the series look a lot like 1 over n squared. So let's try comparing this series to 1 over n squared. As always, we should check if the terms are positive as n approaches infinity, and this is true. 2 to the 1 over n squared is going to be greater than 0 for n greater than or equal to 1. And we know that the series, the sum of 1 over n squared, converges since it's a p-series with p equals 2. So to compare our given series to this one, we take the limit as n goes to infinity of 2 to the 1 over n squared divided by 1 over n squared. If we invert that fraction 1 over n squared in the denominator, we get that the n squares cancel, and we're looking at the limit as n goes to infinity of 2 to the 1 over n, which is 1. And certainly 1 is a finite number which is greater than 0, so we can conclude that both of these series converge. Let's also try this example, the sum of 1 plus 1 over n cubed over 3 to the n. So as n goes to infinity, again 1 plus 1 over n cubed looks complicated, but it's heading towards 1 at a rapid rate, because as n goes to infinity, 1 over n goes to 0. So we would expect this series to behave a lot like the sum of 1 over 3 to the n. At least the terms as n approaches infinity look very like 1 over 3 to the n. Now the terms are positive for n greater than or equal to 1, so it's legitimate to apply the limit comparison test here. I'm going to compare the series to the sum of 1 over 3 to the n, and I know all about this series. I know it converges because it's a geometric series with r equals 1 over 3, which is less than. Okay, so let's apply our limit comparison test. We take the limit as n goes to infinity of an over bn, which is the limit as n goes to infinity of 1 plus 1 over n cubed over 3 to the n divided by 1 over 3 to the n. And cancelling the 3 to the n's, we get the limit as n goes to infinity of 1 plus 1 over n cubed, which is 1, and therefore we can conclude that both series converge because the limit is a finite number which is greater than 0 and of course less than infinity. Let's try a last example, which is certainly the most offbeat example we've looked at so far, the sum of sine of pi over n from 1 to infinity. Now for the first time we have to think a little bit about whether the terms of this series are positive, but for n bigger than 1, pi over n is some angle between 0 and pi, so sine of pi over n is going to be greater than 0. So I can apply the limit comparison test if I can think of some series to compare this given series to. Now remember back in Calc 1 we had that the limit as x goes to 0 of sine of x over x equals 1. And here the x would be pi over n, so the limit as n goes to infinity of sine of pi over n would be equal to 1. So we could compare this series to the series the sum of pi over n. And when we think about that series, it's pi times the sum from 1 to infinity of 1 over n. I can pull that pi out of each term, and I get pi times the harmonic series, which I know diverges. Let's run a comparison test. The limit as n goes to infinity of an over bn is the limit as n goes to infinity of sine pi over n divided by pi over n. And if I let x equal pi over n here, that's the limit as x goes to 0 of sine of x over x, which I know is 1. And certainly 1 is a finite number between 0 and infinity. It's not equal to 0, so we can conclude that both of the series diverge.